Hi everyone, in this video we're going to be looking at some calculus applications. In particular we're going to be looking at finding optimum situations using calculus. So this is really useful when we're trying to find maximum profits, minimum costs, any kind of situation where you can model with some algebraic equation. We can use calculus to find maximum and minimum values. So least cost, least effort, lowest inflation, minimum pain, all of the things that we've got here are things where calculus becomes really helpful. So let me do 3 examples here. Start off with something really simple. What should be the dimensions of a rectangular shape of perimeter 20 centimeters if its area is to be a maximum? So we want to maximize this area here. So I have to start off with using some variables here. So let's say that side there is x and that side there is y. So the thing that we're trying to find a maximum value for is x times y. Now the problem with this expression is it has 2 variables in it, x and y. So we need some extra information in here to help us solve this problem, and this bit of information here is going to help us. The fact that the perimeter is 20 means 2x plus 2y is equal to 20. Alright, so I'm going to rearrange this equation here so I get one variable on its own, and I'll choose y. I could have chosen x to get on its own, but I'll choose y. So I get y is 10 minus x, dividing both sides by 2. Okay, so now what I'm going to do is substitute that value of y back into this expression that we have for the area that we're trying to find a maximum for. So the area of the rectangle is x times y, and we know y is 10 minus x. Okay, so that gives us 10x minus x squared. So there's the area in terms of x. Now if we think about that graph, I could write it like this if I wanted to, x 10 minus x. So this is a quadratic graph. The negative means that we're upside down, or concave down if you like. For using it in factorized form like this, I can see that the x-intercepts are 0 and 10. So it's going to be doing something like this, upside down. We're trying to find this point right here. So this is a graph of the area against x. So you probably can see from the symmetry here what the value is going to be. That value right there, I reckon, is going to be 5 when x is equal to 5. That's just looking at the graph, but you can see the situation here, that as we move along, the area is getting bigger and bigger and bigger. It reaches the biggest possible value, and then the area starts to go down. Well, calculus is going to be really helpful here, because what we really want to find, that point right there, is where the slope of the curve is 0. Okay, in other words, that is where the derivative is equal to 0. Okay. So let's go back to our function now and do the derivative. This is actually dA dx, the rate of change of a with respect to x. So looking at this expression here, it's going to be 10 minus 2x. Okay, and we want to know when the slope is equal to 0. So if we add 2x, divide by 5, you can see that x is equal to 5 centimeters. If we go back up to what we said y was 10 minus x. So our y value here is 10 minus 5, which is also 5 centimeters. So x and y are both 5 centimeters. So that's the dimensions of our rectangular shape to get a maximum area. The question might say, what is actually the maximum area? So the maximum area here is x times y, which in this case here is 25 centimeters squared. Here's some hints on doing these problems. Always draw a diagram. It's really helpful to get a diagram going to see what's going on. Identify the variable that's to be maximized and minimized. So on the one that we just did, it was the area. If the equation has 2 variables, we need to look at another equation that helps us to substitute. Like in the one that we just had, we had 2x plus 2y equals 20. When you have c in terms of one variable, like we just did, we then want to find when dc dx is equal to 0. or in our case it was dA dx is equal to 0. Now this one here, use your knowledge of what the function must look like to see whether it's a maximum or minimum. And that's that one here as well. So I could see from the graph of this one here that we had a maximum value. Another way to work out if you've got a maximum or a minimum is to just look at what's going on at the derivative either side of your stationary value. So what do I mean by that? If here's all the derivatives, dA dx, and we've found that 5 is where the derivative is equal to 0, what's going on here and what's going on here? So let's take a value like 4 before the derivative and substitute it into the derivative. Remember, the derivative is 10 minus 2x. So 10 minus 2 times 4, 10 minus 8 is 2. So it's actually positive. The slope of the curve is actually going up before 5. If we choose a value like 6, or we could have chosen 5.1 or anything after 5 actually, substitute that into 10 minus 2x, 10 minus 12 is negative 2. You can see that here the slope is negative, so it's going down. And we know right at 5 the slope's 0. Just looking at this little diagram here, I can see it's going up, 0, and then down, so I can clearly see that 5 is a local maximum. Okay, that's one way of seeing whether you've got a minimum or a maximum in one of these problems. Okay, here's another classic problem that I'm going to lead you through. This one here is very, very similar. In this case here, we've got some fencing, and I've got 200 meters of fencing, and I want to build an enclosure that has a maximum area. But in this situation here, there's a river on one side of my my enclosure, so I don't need any fencing on the river side. So if I call this X and this Y, I don't need any fencing over there. So we want to find the maximum area. So let's go through the steps. The maximum area here, again, is X times Y. In this case, we know 2x plus y is 200. We have 200 meters of fencing. So this plus this plus this has got to add to 200. Following the steps, y is 200 minus 2x. So then our area is x times 200 minus 2x, which is 200x minus 2x squared. Again, you can get a sense for what this area looks like because this is a quadratic. It's going to be upside down. So you could draw this graph here. I'm going to show you the graph. There it is there, 200 minus 2x squared. So you can get an idea of what's going on. That's the point we're looking for right up there. And right at that exact point, the slope is equal to 0. So we want to find when the derivative is equal to 0. So a dash, or dA dx, is 200 minus 4x. Okay, so this is very similar to the last one. Add 4x to both sides, divide by 4, and we get x equals 50. When x equals 50, the y value is 200 minus 2 times 50. 200 minus 100, which is 100 meters. So in this case here, the best dimensions that we could use to get the most area out of this situation is when we make x, this is 50, and this one here is 100, kind of like I've drawn it, except this front fence here would be double the length of that one there. Okay, then we'd use all of our fencing and we get a maximum possible area. Again, the question might say, what is the maximum possible area? So in this case here, we're talking about meters. It'll be 5,000 meters squared would be the maximum area. Looking at our graph, I can clearly see that we've got a maximum value. Third and final example here. Now we've got a real model for what's going on with a company and their profit. And we want to find, in this case, the maximum profit. Now X in this case is the number of items that the company produces, and P is their profit. So this is a cubic and I've drawn it, so here it is here. You can see the answer's already there. So we actually start off, when we produce no items, we've got a profit of negative 1,000. As we produce more items, and that might be some startup costs. Okay, as we choose more items, you can see the profit gets bigger and bigger and bigger until it reaches a peak, and then it goes down. And after we're producing this many items here, around about 50, you can see the profit then goes into the negative. So we definitely wouldn't want to produce any more than that. In fact, we want to produce this many. Okay, so what we're trying to find is that value of x right there where the maximum value is, and the slope of the curve is 0. So let's use calculus to do that. It's dp dx in this case. So negative 3x squared plus 60x plus 900. That is the derivative, and we want to find when that is equal to 0. Now I can see here that we've got a common factor of 3, so I could take 3 out, plus 300, and then just to make this easier to solve, I could times everything by negative 1. So we've got x squared minus 20x minus 300 equals 0. I think it's just easier, okay? Because when we try and factorize it, it just makes it easier if there's an x squared at the front there. So we want two numbers at times to give me 300 and add to give me negative 20. I'm thinking 30 and 10. Negative 30 and plus 10 will get it to us. And you can always check that. X squared plus 10x minus 30x is minus 20. And negative 30 times plus 10 is negative 300. So I've got it. Cool. So x must be 30 or negative 10. Straight away, we can't create negative 10 items, so our answer has got to be x equal to 30. Now in this case here, it is trickier to know whether this is a maximum or minimum. I mean, we hope from the problem that that's given us a maximum, but we want to really show it. If we didn't have our CAS, we couldn't draw this thing here. So I can clearly see what the maximum value is, 30. I could see that one. But if you wanted to prove it, using the technique I showed you before, here's 30 as our maximum value that we've found, or a stationary value. What's going on either side of 30? So what you do is you substitute a number like 29 into the derivative, this thing here. Negative 3 times 29 squared plus 60 times 29 plus 900. You'd find that the number that you get out of there is positive, meaning it's going up. You'd find if you put in a number of like 31 into that equation up there, you'd get a negative number. So the slope is going down. So then you can see that the value you found is a maximum value. And again, if the question said, what is the profit? You could do that also. And all you need to do is substitute x equals 30 back into the original equation for the profit. And if you did that, you would get $26,000 for the profit when we produce 30 items.